Hello friends! I want to show you my development. It's my multistage boost converter. The schematic is here. Core of the converter is pulse frequency modulator, made from logic IC CD41-106. This IC consists 6 inverters with Schmitt trigger. Here we see the first logic element that acts as pulse frequency modulator. From the output on input we have negative feedback R2. I know mean negative feedback, but rather feedback. When output becomes high, the voltage flow through the resistor and charge capacitor C1. When the capacitor have enough voltage and voltage becomes threshold of input trigger, the voltage on output becomes low and resistor discharge through, and the capacitor discharge from this resistor and voltage becomes low. When low threshold occurs and voltage becomes low enough, the trigger switch to high, and this process runs periodically and continuously. The output voltage and the output frequency and pulse duration have dependence on input DC voltage. Average DC voltage on the input. So when voltage decreases, so the output frequency and pulse duration also decrease. And when input voltage is small, on the output we have very short pulses and very long delays. To drive output switches we need enough current. So to amplify output current I use 5 inverters in parallel. But output current is not enough to directly drive of these two switches. So I use 2 transistors, 2 emitter followers to amplify output current. To reduce negative spikes from gates of first or the second stages I use Schottky diode, because negative spikes may cause incorrect work of this schematic. For the supply of modulator you can use optionally low dropout output linear regulator or simply small coil. With low dropout output linear regulator you will have more stability of output frequency. But this device can run without LDO regulator. I connect, in my schema I use only coil. Here we see the first stage. The first stage consists of switch and diode output capacitors. When the first switch turns on, the energy recovered in coil. The energy stored in coil. When switch turned off, all the energy flew through the diode into two capacitors. This capacitor have small capacitance. This capacitor suppress high frequency spikes with high current, so it decrease heating of this electrolytic capacitor and increase efficiency. The second stage is the same as the first, but here we have fast switch diode and two capacitors, one with small capacitance to reduce high frequency spikes and one electrolytic capacitor. Here we have two coils. These coils becomes maximum output power. When inductance is too high, the output voltage the output power will be low. You can read about modes of boost converter in the internet. There are critical conduction mode, continuous conduction mode, and discontinuous conduction mode. Here we should have critical conduction mode or discontinuous conduction mode. I use two stage because when we have one stage to boost voltage from 12 volts to 200 volts, we have very small, very short pulse on the output, and it reduces efficiency. I have experience. I made some DC-DC converter from 12 volts to 200 volts, and the efficiency was bad, roughly 70%. To control output voltage, we have two loops, two negative feedback loops. The first loop consists two diodes, so the maximum output voltage roughly 49 volts, and the second, and it also the main control loop, consists two Zener diodes with common voltage 200 volts. All these two signals go through the one wire to linear regulator. No stabilizer, but linear switch, valve Q1 It's a bipolar transistor that controls average input DC voltage of this modulator. Here we see low pass filter and threshold regulator. This resistor R4 set the minimum feedback current. Now it's roughly 250 microamperes. Let's see at the device. Here we see the modulator, a logic gates and the transistor that acts in feedback. Here we see the first switch with diode and capacitor, and the second switch with diode and capacitors. Now the oscilloscope connects to the output of driver, to the emitters of transistors. Our device now is running without any feedback because I switch off the first coil. As we see, we hear the frequency 55 kHz and the pulses. Roughly 75% of the pulse is positive and roughly 25% of pulse is negative. Now I load my converter on the bulb. Here is output, here is the input power. Here we see the output voltage and the output current. The output current is 100 milliamperes. The output voltage is 194 volts. Input voltage is 12 volts. Let's see at the drain of the first MOSFET, the first switch. Here we see the green line is the gate voltage and the red line is the drain voltage. Here we see when the switch turns off, in coil appears high voltage. I mean additional voltage. This pulse means that all the power from the coil flew into load. When all the power gone into the load, the pulse becomes low. Here we see free oscillation between the end of the pulse and the new pulse on the drain, on the gate. In this period, no energy flow into or from the coil. I have in my converter two coils. The first coil is 33 microhenries and it has resistance 0.05 ohms. I have the second coil, 470 microhenries, with impedance of 1 ohm. As a result, I calculated the efficiency. It's roughly 85%. Let's look at the second stage. Here we see that the voltage on the drain, the second stage, the second switch, is much higher than on the first switch. Here we see the same picture. The active period when all the energy flew into the load, and the period where no energy restored or recuperate. I mean, no energy flew into coil or from coil. Thanks for watching, friends.